Hello students, this is Nikilian, Assistant Professor, Department of Civil Engineering, AJT, Mangaluru. So in our previous two sessions, I had discussed about limit state of collapse in flexure. So today in this session, I am going to discuss about limit state of collapse in shear. So as per your syllabus, this is module 4. So when we consider a prestressed concrete member, the shear stresses are distributed across the depth of member is assumed to be linear and is the function of shear force and the properties of the cross section of the member. The effect of shear stress is to induce principal stresses on diagonal plane. The strength of concrete subjected to pure shear is nearly twice that in the tension. Hence, local failure first appear in the form of a diagonal tensional crack in regions of high shear stresses. So in pre-stressed concrete members, the shear stress is induced due to two reasons. In that first one is the direct stresses in the axial direction of the member when horizontal or axial pre-stressing is done, and the second one is the compressive stress in the direction perpendicular to the axis of the member in addition to direct axial stress when transverse vertical pre-stressing is done. So when we consider a prestressed concrete member, in a prestressed concrete member, the diagonal shear stresses are induced due to horizontal prestressing and vertical prestressing. So in prestressed concrete member, the direct stresses are compressive and hence the magnitude of the principal tensile stress is eliminated or it is considered as zero. So under the working load, both major and minor principal stresses are compressive stresses, due to which the risk of diagonal tension crack in concrete is eliminated, and we can calculate what is the diagonal stresses developed in the pre-stressed concrete member. So let us see how we can calculate the stresses developed in the diagonal plane. So the maximum and minimum principal stresses developed are given by. Let us consider a rectangular section. So this is a rectangular section. So in this rectangular section, let us consider a small elemental strip. This is a small elemental strip. So when this small elemental strip is subjected for a horizontal pre-stressing and vertical pre-stressing. So here in this figure, let f of x be the horizontal pre-stressing and f of y be the vertical pre-stressing. So horizontal pre-stressing and vertical pre-stressing means the cables are pulled in horizontal direction as well as the cables are also pulled in vertical direction. That means the cables are provided in horizontal direction as well as in vertical direction. So due to this f of x and f of y, here we can see it is showing the diagonal stresses developed in the elemental strip. So this is a diagonal tension or diagonal stresses developed in the member. So this diagonal stress which is developed in the member is also called as principal stresses. So this principal stresses can be calculated using this equation. So F is equal to f of x plus f of y divided by 2 plus or minus 1 by 2 square root of f of x minus f of y whole square plus 4 tau v square, where tau v is the shear stress. Tau v is the shear stress in the member, and f of x is direct stress in axial direction due to horizontal or axial pre-stress. So f of x can be calculated using the formula f of x is equal to px by a plus px e by I plus m into y by I. Similarly, f of y is vertical stress in vertical direction due to vertical or transverse pre-stress, and f of y can be calculated using the formula f of y is equal to py by a plus pye by I plus my divided by I. So using this equation we can calculate what is the stresses developed in the member due to vertical pre-stress and horizontal pre-stress, which are responsible for developing the principal diagonal tension or principal diagonal stress. So note, so to calculate what is f of x and what is f of y, we have some boundary conditions. So let us consider note. So if I want to calculate f of x at the support, then f of x is equal to px by a, where px is the horizontal pre-stress component of axial or horizontal pre-stressing force. So px can be calculated by where px is equal to p in case of straight tendons and px is equal to p cos alpha in case of inclined or curved tendons. So remember this, at support f of x, that is horizontal pre-stress, is equal to px by a, where px is horizontal pre-stress component of horizontal pre-stressing force, where px is equal to p in case of straight tendons and px is equal to p cos alpha in case of inclined or curved tendons, and a is the gross cross-sectional area of the concrete. Suppose stress in steel, that is f of x, stress in steel, diameter of steel wires, thickness of web of a flanged section, and spacing of steel is given. Then the vertical pre-stress f of y can be calculated by f of y is equal to f of x into pi d square by 4 into tw into s. So that was about how to calculate f of x and f of y. So we know that tau v is shear stress developed in the section. Then how to calculate shear stress for different cable profiles. So to calculate shear stress for different sections and conditions. For a rectangular section with straight tendon, maximum shear stress acting at the support section tau v is equal to 1.5 v by bd, where v is shear force at the section, b is breadth of the rectangular section, and d is overall depth of the rectangular section. So here shear force means it is not the factored shear force. For a rectangular section with inclined and curved cables or tendons. So the first one was a rectangular section with straight tendons, and second one is a rectangular section with curved tendons or parabolic or circular tendons. So maximum shear stress acting at any section tau v is equal to 1.5 v by bd, where v is equal to vl minus p alpha, p sin alpha. In previous case it was shear force at a section, and here v is equal to vl minus p sin alpha, where vl is equal to shear force due to dead load and live load at any section xx, and vl is equal to wl by 2, that is shear force at the support for simply supported beam, and w is equal to wg plus w cube, that is live load plus dead load of a section, and p sin alpha is equal to vertical component of axial pre-stress. For parabolic cables, slope at one end alpha is equal to 4h by L into 180 by pi in degrees. So if I want to calculate the slope of a parabolic cable, in terms of radian, then alpha is equal to 4h by L. For circular cables, slope at one end, alpha is equal to L by R into 180 by pi. So this we will get the slope in terms of a degree, and if I want to calculate the slope in terms of radian, then alpha is equal to L by R. So while solving the problems, we will calculate the value of slope in terms of radian. Hence, it is sufficient if you remember 4h by L for parabolic cable and L by R for circular cable. And here R is equal to radius of a cable. If the radius of a cable is not given, then we can calculate the radius of cable using the formula 1 by 2 into L square by 4h plus h. So we are going to use this equation when the radius of cable is not given. If the radius of cable is given, then we can directly substitute the value here and we can calculate what is the slope of a circular cable. So here H is central dip of the cable, that is the rise or dip of a cable, and L is span of a beam. So note here H and L are same units. So H is in meter as well as L is in meter. Now how to calculate the values of shear stress for a flanged section. So flanged section means it may be a I section or a T section. So the previous one was to calculate shear stress for a rectangular section with straight tendons and inclined tendons, and the second condition is to calculate shear stress for a flanged section. So for flanged section, maximum shear stress acting at any section XX, tau V is equal to Fxx into Ay bar divided by Ib, where effective shear force at the section XX, Fxx is equal to VLxx minus P sin alpha xx. So shear force due to total load at section XX is equal to VL at section XX, and vertical component of axial pre-stress at section XX is equal to P sin alpha at section XX, where P is effective pre-stressing force. For parabolic cables, slope of the cable at section XX, alpha is equal to 4h by L minus 8hx divided by L square. If we use this equation, we will get slope in terms of degrees, and in this equation H is central dip of the cable and L is span of the beam. X is the distance of section XX at which shear force is calculated. A is area of cross section of the section under consideration. Y bar is distance between center of gravities to center of gravity of area considered from center of gravities. I is moment of inertia about axis of bending, and B is width of the section under consideration. So these are the equations you should remember. So you should remember this equation, and in this equation you should remember what is f of x, how to calculate f of x, how to calculate f of y, and how to calculate tau v. So these three things you should remember, and you should remember the conditions to calculate tau v when it is a rectangular section with straight tendons and curved tendons, and if a section is flanged section with a straight tendon or a curved tendon, then how to calculate shear stress tau v. So these are the things you should remember. If you remember this equation, and if you remember how to calculate f of x, f of y, and tau v, then easily you can solve the given numericals. And here all the numericals which will be given in your exam will be a direct question. Now let us consider an example. So the first example is a prestressed concrete beam. Span is 10 meter of rectangular section, 120 mm wide and 300 mm deep, is axially prestressed by a cable carrying an effective force of 180 kN. The beam supports a total uniformly distributed load of 5 kN per meter, which includes self-weight of the member. Compare the magnitude of principal tension developed in the beam with and without axial prestress. So in this question, it is given that a prestressed concrete beam and the span of a beam is 10 meter and the beam is of a rectangular section. The width of the beam is 120 millimeter and depth of the beam is 300 mm. So this rectangular prestressed concrete beam is axially prestressed by a cable, and this cable is carrying an effective force of 180 kilonewton. So here it is axially prestressed means the pre-stress is applied in horizontal direction, that is f of x, and the cables are carrying a pre-stressing force of 180 kilonewton and it is an effective pre-stressing force, and the total load which is acting on a beam is in the form of uniformly distributed load, and this is including UDL, this is including dead load and live load. So the total UDL acting on a beam is 5 kN per meter. So in this question, they have asked us to calculate the magnitude of principal tension developed in the beam with and without axial prestress. So what is the tension, principal tension developed in the beam when there is no prestressing is done and when the prestressing is done? So you remember the equation. So this is the formula we need to use. So here I told you this is prestress in horizontal direction, prestress in vertical direction. So in the question they have not given anything about vertical or transverse prestress. Therefore this term is 0. Fy will be eliminated because they have not given anything about vertical prestress. They have given the value of f of x. They have given what is the pre-stressing force that is applied in axial direction. That is, in axial direction, an effective pre-stressing force of 180 kN is applied. Therefore, we can calculate the value of f of x. So this formula will become f of x by 2. This will be 0 because they have not mentioned anything about vertical pre-stressing. So the final formula will be f maximum or minimum is equal to f of x by 2 plus or minus 1 by 2 into x square plus 4 tau v square. So this will be the final formula. So in the question they have given two conditions. The first condition is we should calculate the principal diagonal tension when there is no pre-stressing is done. So where there is no pre-stressing is done means we are not going to consider this f of x. So no pre-stressing is done. Therefore f of x will be equal to 0. Only this term remains. So for the first condition, f maximum or minimum is equal to square root of 4 tau v square because no pre-stressing is done in the first case. So for the first case, f maximum or minimum is equal to square root of 4 tau v square. For the second case, when the member is subjected to axial pre-stress, then the formula will become f maximum or minimum is equal to fx by 2 plus or minus 1 by 2 square root of f x square plus 4 tau v square. So these are the two formulas which we can use for the example 1. Now you know what's the formula to calculate the principal tension developed in the beam with and without the axial pre-stress. So first I will calculate what is the cross section area of a given member. So cross section area A is equal to 120 into 300, that is 36 into 10 to the power of 3 millimeter square. Moment of inertia I is equal to 27 into 10 to the power of 7 mm to the power 4. So it is a rectangular section. Therefore, for the rectangular section, the moment of inertia is BD cube by 12. Therefore, I is equal to 27 into 10 to the power of 7 millimeter to the power 4, and WD is equal to 5 kilonewton per meter. The W is the total load acting on a member including self weight as well as live load. So we all know that shear force is maximum at the support and it is minimum at the midspan, or it is minimum where the bending moment is maximum. So for a simply supported beam, what will be the shear force? So for a simply supported beam, shear force is nothing but it is the reaction at the supports. So it is a simply supported beam in the form of a UDL. Therefore, reactions Ra and Rb will be equal to WL by 2. So WL by 2 is nothing but it is the support reaction, which is nothing but shear force at the support. So shear force at the support is nothing but it is the reaction of the supports. So shear force at support V is equal to WL by 2. So W is total weight, 10 is span of a beam, it is given by 2, which is equal to 25 kilonewton. So shear force at the support section is equal to 25 kilonewton. Then maximum shear stress at support. So maximum shear stress at the support. So remember it is a rectangular section. So for rectangular section with straight tendons. So in the question they have not mentioned whether it is a straight tendon or a parabolic tendon. So let us consider it as a straight tendon because they have not mentioned any angle or any eccentricity at the center or at the supports. So let us consider it as a straight tendon. So to calculate the maximum shear stress at the support section for a rectangular section with straight tendon, we have the formula tau V is equal to 1.5 V divided by BD. And remember here, D is not effective depth, so it is capital D, which we should consider overall depth of the section. So considering the formula, maximum shear stress at support tau V is equal to 3V by 2 into B into H. So 2 by 3 is nothing but it is 1.5. Alright, so you can directly substitute 1.5 V divided by B into D. So 2 by 3 by 3 into V by 2 BH is same as same equation. So substituting the values of V, B and H. So H is overall depth. So 3 by 2. So 3 by 2 is 1.5. So V is 25 to 10 to the power of 3. V is nothing but shear force at the support. It is 25 kilonewton. Here it is 25 to 10 to the power of 3. So kilonewton is converted into Newton. B is width of a beam. So width of a beam is given, that is 120 millimeter, and H or capital D, it is depth of a beam, that is overall depth of a beam. So overall depth of a beam is given, it is 300 millimeter. So substitute the values, and by solving this equation I will get the maximum shear stress at the support tau V is equal to 1.05 Newton per millimeter square. So this is the maximum shear stress that will develop at the support. Now coming to the first condition. So what is the first condition? compare the magnitude of principal tension developed in the beam without and with axial pre-stress. So first I am going to consider what is the magnitude of principal tension developed in the beam with without axial pre-stress. This is the principal stresses developed in the member without axial pre-stress. So without axial pre-stress means f of x is equal to 0 and f of y is equal to 0. There is no pre-stressing done in horizontal direction as well as in vertical direction. When f of x and f of y is equal to 0, the equation will become plus or minus 1 by 2 square root of 4 tau v square. So plus or minus tau v is equal to 1.05 Newton per mm square. So principal stresses when there is no pre-stressing is done is equal to 1.05 Newton per millimeter square. So axial pre-stress. So I will calculate axial pre-stress to calculate the principal stresses developed in the member when the member is subjected for axial pre-stressing. That is first case, that is to calculate the principal tension developed in the beam with axial pre-stress. So here it is given that there is a cable which is axially pre-stressed. So there is a cable which is axially pre-stressed by an effective force of 180 kN. So I will consider that case to calculate the principal stresses developed in the member when it is subjected to horizontal pre-stressing. So when it is subjected to horizontal pre-stressing, we know the formula is f of x by 2 plus or minus 1 by 2 square root of f of x square plus 4 tau v square. So here f of y will be 0 because in the question they have not mentioned anything about vertical pre-stressing. Therefore f of y is equal to 0. So here f of x, that is axial pre-stress or horizontal pre-stress, that is equal to f of x is equal to p by a. See here at support f of x is equal to px by a or p by a. The value of p is given, that is 180 kilonewton. Here it is given carrying an effective force of 180 kilonewton. So p is equal to 180 kilonewton. In terms of Newton, it is 180 into 10 to the power of 3 Newton divided by a. So a is cross section area of the member. So cross section area of the member we have calculated, that is 36 into 10 to the power of 3 millimeter square. So substitute the value of a in the equation. Therefore axial pre-stress f of x is equal to 5 Newton per mm square. So this is the axial pre-stress that is induced in the cable. Therefore maximum and minimum principal stresses is equal to f of x by 2 plus or minus 1 by 2 square root of f of x square plus 4 tau v square. So substitute the values of f of x and tau v. So f of x is 5 by 2 plus or minus 1 by 2 f of x square, that is 5 square plus 4 into tau v. So tau v we have calculated in previous step, that is 1.05. So substitute the value of tau v, that is 1.05 square. Therefore maximum and minimum principal stress is equal to 2.5 plus or minus 2.73. So solving this I will get 2.5 plus or minus, solving this I will get 2.73. So if I consider it as maximum, then it is 2.5 plus 2.73, that will be plus 5.23 Newton per mm square, that is compression. And if I consider it as minus, then it will be 2.5 minus 2.73, which is equal to minus 0.23 Newton per mm square. It is a tensile stress. So the maximum stress developed in the beam or a member is plus 5.23 Newton per mm square, and minimum stress developed is 0.23 Newton per mm square. Hence, with axial pre-stress, the principal tension is reduced by 1.05 is the principal stress without axial pre-stressing, and 0.23 is the stress induced in the member with pre-stressing. So 1.05 minus 0.23 divided by 1.05 into 100, that gives 78%. So this 78% is indicating that with axial pre-stress, the tension reduced in the member is 78%. That is, it is beneficiary to provide axial pre-stressing in a beam. So if we provide axial pre-stressing in a beam, then the principal tension will be reduced by 78%. Hence, beam will be more stable than previous condition, or the beam will be more stable compared to the member without pre-stressing. Now let us consider the second example. For the beam in example 1, instead of axial pre-stressing, a curved cable having an eccentricity of 100 mm at the center of the span and reducing to 0 at the support is used. The effective force in the cable being 180 kN, estimate the estimate the percentage reduction in the principal tension in compression with the case of axial pre-stressing. So here it is a rectangular section of size as of previous problem. That is, the cross section of a beam is 120 mm by 300 mm and span is 10 meter. So for the same beam, the beam is provided with a cable which is a curved cable having an eccentricity of 100 mm at the center and 0 at the support. So for this beam, we need to calculate the percentage reduction in the principal tension in comparison with the case of axial pre-stressing. So the procedure is same. The only difference is there it was a straight cable and here it is a curved cable. So first I should calculate what is the shear force developed at the support. Then I should calculate what is the maximum shear stress at the support, and I should calculate what is minimum or maximum principal tension developed in the member. So slope of the cable at support, that is 4E by L. So see here, for a rectangular section with inclined and curved cable, that is parabolic or circular cable, the maximum shear stress at any section tau V is equal to 1.5 V by divided by BD. Then V is equal to VL minus P sin alpha. So VL is the shear force due to live load and dead load. VL is the WL by 2. So here it is given as VL minus P sin theta for V. So here the angle is very small, that is alpha is very small, hence we can consider this equation as V is equal to VL minus P alpha, because the angle or the deflection is very small, hence this will become P alpha. So remember this, V is equal to VL minus P alpha. Sin alpha is equal to alpha. So first I will calculate slope of the cable at support. So slope of the cable at support can be calculated using the equation 4E by L. So 4 into E is eccentricity and L is span of a beam. The span of a beam is 10 meter, and in terms of millimeter it is 10 into 1000, which is equal to 0.04 radian. Therefore, the vertical component of pre-stressing force is equal to 180 into 0.04. So 180 is the effective force in the cable. So it is 180 into 0.04 or P into alpha. P into alpha, that is equal to 7.2 kilonewton. Horizontal component of pre-stressing force is equal to 180 kilonewton. Then net shear force V is equal to 25 minus 7.2, which is equal to 17.8 kilonewton. So it is a curved cable. So in a curved cable, the net shear force at the support V is equal to VL minus F sin alpha. But F sin alpha is equal to alpha, therefore V is equal to VL minus P alpha. So P alpha is vertical component of pre-stressing force, that is P is 180 into alpha. So P alpha is equal to 7.2 kilonewton and VL is 25, that is WL by 2. So that we have calculated in previous problems. See here, shear force at support 5 into 10 by 2 WL by 2, that is equal to 25 kilonewton. So VL is 25 minus P alpha or F alpha. VL minus F alpha, 25 minus 7.2. So here you can see F alpha. F is 180, it is given here, and 0.08 is the slope of a cable. So slope is very small, hence sin alpha is equal to alpha. So that will become P or F alpha, which is equal to 7.2. Net shear force will be equal to shear force due to live load and dead load, that is 25, minus shear force due to vertical component, that is 7.2. So therefore net shear force at support is equal to 7.8 kilonewton. So maximum shear stress 1.5 V divided by BD. So the same equation, 3 by 2 is 1.5. So V divided by VB into H, where H is overall depth of a beam. So 3 by 2, which is 1.5 into 17.8. V is 17.8, that is net shear force at the support is 17.8 into 10 to the power of 3. Here it is in kilonewton and here it is in Newton. B is 120 and H is 300. Therefore, maximum shear stress is equal to 0.74 Newton per millimeter square. And axial pre-stress F of X. So we need to calculate what is the minimum and maximum principal tension when the member is subjected for axial pre-stress. So for that we need what is F of X. So F of X is equal to P by A. So the value of P is 180. It is given horizontal component of pre-stressing force is 180 kilonewton and cross section area is 120 by 300. Therefore axial pre-stress F of X is equal to 5 Newton per mm square. So 5 F maximum and minimum is equal to 5 by 2 plus or minus 1 by 2 square root of 5 square plus 4 into 0.74 square is equal to 2.5 plus or minus 2.62, which is equal to plus 5.12 minus 0.12. So here 5 by 2 is nothing but it is the value of F of X into 1 by 2. So this is the equation we are using to calculate F of X. To calculate F maximum or F minimum, we are using this equation. So we have calculated F of X, that is 5. So F of Y is 0 because they are not given the value of vertical pre-stress. So this value is 0 and they have given there is an axial pre-stress, that is F of X. So F of X is equal to 5. So 5 by 2 plus or minus half into 5 square plus 4 tau v square. So same thing is been done here. F of X by 2 plus or minus 1 by 2 F of X square plus 4 into tau square. So tau is 0.74, maximum shear stress, f of x is 5. So F maximum and F minimum is equal to plus 5.12 and minus 0.12 Newton per millimeter square. So if we compare with and without pre-stressing, in comparison with axial pre-stressing, the percentage reduction in principal tensile stress 0.23 minus 0.12 divided by 0.23. So this 0.23, it is the shear stress, sorry, it is the principal shear stress or principal tensile stress obtained when there is no axial pre-stress. So that we have calculated in previous problem. So principal stress without axial pre-stress. So that gives us 48%. Similarly, when compared with a beam without any pre-stress, the percentage reduction in principal tension 1.05 minus 0.12 divided by 1.05, which is equal to 88.5. So this also we have calculated in previous problem. You can see. So 0.23, 1.05. So we are comparing these values with the values of straight cable with the values of a curved cable. So these are the comparison values between a parabolic or a curved cable and a straight cable. So again I am telling you the difference between first problem and second problem was, in the first problem the cable was a straight cable, and in the second problem the cable was a curved cable. And what we have done is we have compared the results of straight cable and curved cable. So this was the result of point 3 was the result of curved straight cable, and point 1 is the result of curved cable. So here we have compared what is the reduction in principal tensile stress when we provide straight cable and when we provide curved cable. Here you can see the results of straight cable. So it is 0.23 minus 0.23 plus 5.23. So that results we have compared here 0.23 and 0.12. This is for curved cable, this is for straight cable. 1.5 and 0.12. So this is 1.5 is the principal stress developed in the member when there was no cable, and this is the principal stress developed in the beam when a curved cable is provided. So 0.12 is the minimum stress developed. Let us consider a third example. A post-tension beam of rectangular cross-section 200 mm wide and 400 mm deep is 10 meter long and carries an applied load of 8 kN per meter uniformly distributed on the beam. The effective pre-stressing force in the cable is 500 kN. The cable is parabolic with zero eccentricities at the support and maximum eccentricity of 140 mm at the center of the span. So first one, calculate the principal stresses at the support. Second one, what will be the magnitude of principal stresses at the support in the absence of pre-stress? So the problem is same as first problem, but the difference is in the first problem it was a straight cable and here it is a parabolic cable. So the section is rectangular section having a cross section area of 200 mm wide and 400 mm deep. The span is 10 meter, and here a beam is carrying a total load of 8 kN per meter, which is in the form of uniformly distributed load, and the cables are subjected for a pre-stressing force of 500 kilonewton. So 500 kilonewton is the effective pre-stressing force. It is the force after occurring of all the losses, and the cable is having an eccentricity of 0 at the supports and the eccentricity at the midspan is 140 millimeter. So for this condition we need to calculate what is the principal stresses developed at the support when there is a pre-stressing of a cable. Second case is what will be the principal stresses developed at the support when there is no pre-stress. So there is no pre-stress is applied. So at that condition what will be the stress developed at the support. So before that we know the equation to calculate F minimum and F maximum. That is, we know the equation or formula to calculate maximum principal stress and minimum principal stress. So in that formula, what are all the datas we need? We need f of x, we need f of y, we need what is tau. So here f of y is not given. So in the question they have not mentioned anything about a lateral pre-stress or vertical pre-stress or transverse pre-stress. They have only mentioned the pre-stress is axial pre-stress. So let us consider and calculate what is f of x, f of y and what is tau. So G is equal to 1.92 kilonewton per meter. So G is nothing but it is the self weight of the member. So self weight of a member is equal to 200 into 400 area multiplied by density of concrete. So density of concrete, let us consider as 24 kilonewton per meter cube. So 24 into 0.2 into zero point 0.4, that gives 1.92 kilonewton per meter. So this is the cross dead load of a section. So Q is the live load which is given 8 kilonewton in the form of UDL, 8 kilonewton per meter. P is the effective pre-stressing force acting in the cable, 500 kilonewton. Eccentricity E is 140 millimeter and L is 10 meter. So we know that for a curved cable, shear force is equal to VL minus F sine alpha or F sine theta. So to calculate theta, that is slope of a cable at support, theta is equal to 4E by L, which is equal to 4 into 140. So E is eccentricity or rise of a cable or a dip of a cable. So 4 into 140 by 10 into 1000. So 10 is in meters, that is the span of a beam is in meters. So converting it into millimeter, that will be 10 into 1000, that gives 0.056 radian. So slope of a cable at the support is 0.056 radian. So vertical component P sin theta or P sin alpha is equal to 500 into 0.056. So 500 is the effective pre-stressing force. So sin theta, so theta is very small, hence sin theta will be equal to theta or sin alpha. In some of the textbooks it is given as alpha. So don't be in a confusion. It will be in some of the textbooks they have directly given as P alpha or P theta. So it is P sin theta or P sin alpha. So here the value of slope is very small, hence sin theta or sin alpha will become theta or alpha. So P sin theta or is equal to 500 into 0.056. So sin theta is equal to theta. Therefore vertical component is equal to 28 kilonewton. Horizontal component P cos theta is equal to 500 into 500 into 0.998, which gives 500 kilonewton. So here it is not required to calculate the horizontal component of shear force. So I am just showing you how to calculate the horizontal component of shear force. It is P cos theta. so which is approximately equal to 500, and vertical component is 28 kilonewton. So maximum shear force at the support due to live load and dead load, it is WL by 2. So W is total load acting on a beam. So 1.2, 1.92 plus 8. So it is W 18 plus 1.92 W into L. L is 10 by 2. Therefore, shear force at the support is equal to WL by 2, which is equal to 49.6 kilonewton. Net shear force or net shear at the support, VL minus P sin theta. So VL is 49.6 minus P sin theta, or P theta is 28. Therefore, net shear force at the support is equal to 21.6 kilonewton. Therefore, shear stress, maximum shear stress tau V is equal to 3V by 2BH, or 1.5 V by 2, 1.5 V by BH. So this is equal to 3 by 2 into 21.6 into 10 to the power of 3 divided by 200 into 400, that gives 0.405 Newton per mm square. So this is the maximum shear stress developed at the support. So now coming to the first condition, maximum and minimum principal tension. So maximum and minimum principal tension when pre-stressing is done, that is considering f of x, the cable is subjected to pre-stressing. So we know the formula, f of x plus f of y by 2 plus or minus half square root of f of x minus f of y whole square plus 4 into tau v square. So here at the support, it is f of x is equal to p by a. That is because they have not given anything about vertical pre-stressing. So it is said that the cables are actually pre-stressed, therefore f of y will be equal to 0. So f of x will be equal to p by a at the support. So direct stress f of x is equal to p by a, which is 6.25 Newton per mm square. So considering the first case, f of x by 2, 6.25 by 2 plus or minus 1 by 2 into f of x square. So this is f of x minus f of y square. So f of y is equal to 0. Therefore f of x square plus 4 into tau v square. So tau v square is equal to shear stress 0.405. So 0.405 whole square, which is equal to 6.275 Newton per mm square, or minus 0.025 Newton per mm square. So this is the maximum shear stress and this is the minimum shear stress when we consider pre-stressing of a cable. Second condition is in the absence of pre-stress. So there is no pre-stressing is done. So no pre-stressing is done means there is no cable in the beam. So no cable means the total shear force or net shear force will be equal to WL by 2. So that is in the absence of pre-stress, vertical shear or maximum shear force at the support will be equal to WL by 2. So WL by 2 is equal to 49.6. So maximum shear force at the support due to live load and dead load, WL by 2. So W is 8. This is live load plus dead load into L by 2. WL by 2 is 49.6 kilonewton. So what will be the principal stresses developed in the member due to this shear force? So maximum and minimum principal stresses is equal to 3 by 2 into 49.6 into 10 to the power of 3 divided by 200 into 400. That is equal to 0.93 Newton per mm square.